Well, good evening, good day, everyone. Welcome back to my channel. So, in this short video, I want to quickly show how we can measure the frequency of an AC signal and also measure the phase angle. Like what we already know, when you have a purely resistive circuit, as you can see from this circuit diagram, this is a laboratory. When you have a purely resistive circuit, the voltage and current are always in phase, as shown from this particular waveform. Both voltage and current are in phase. That is, when the voltage gets to its peak, the current is getting to its peak at that same time. When the voltage goes and runs to zero, the current waveform also runs and goes to zero at the same time, and so on and so forth. That is for purely resistive circuit. But when circuit becomes inductive, then the voltage will lead the current by angle theta, which is the phase angle. Then when we talk of the capacitive circuit, the current will lead the voltage by an angle theta, which is called the phase angle. So in this experiment, I just want to show how we can measure the phase angle, because when you look at this, the instruction on this experiment is a laboratory in the university. So the only critical point or the difficult parameters to measure is the frequency and the phase angle. Every other thing you can just measure them like what you are already familiar with. So this is the circuit diagram as shown in figure 1.3. Here we want to the resistor value is set to be 10 kilo ohms. Capacitor is set to be 0.01 microfarad. The amplitude or the signal, the sinusoidal waveform is set as 2 volt peak to peak, and the frequency of 500 Hz, DC offset of 0 volt. So we want to quickly launch our LT Spice. So for the sake of those who may not know how to patch up this circuit, I'm going to delete this circuit and couple them afresh. I want to delete this circuit and couple them afresh so that we will start afresh. So having launched your LT Spice, you can see your components are already here. So we have the resistor. When you click on it, you right Ctrl R to rotate, then you drop it. You go and click your capacitor, then you drop it. Then the next one is to pick your voltage source. You go to component and you click on it, you type voltage. The voltage supply will come out. Click on OK and you drop it. So to connect the circuit together, you click on this wire and you click on the wire, then you virtually wire everything together. I've done this. So connect everything together. That will be all. But we must not forget to put our ground. This, unlike a Pro Tools, in which at times you may not even put a ground in your Pro Tools design and the system will still run, but in the LT Spice it is not going to work. As a matter of fact, the system will keep giving you an error. So you must not forget to put your ground. And now we get a ground. It's simple. So how to get your ground is simple. To get our ground, you go to, this is the ground. So let me go click on the ground, drop it anywhere. Don't forget to connect it together with the circuit. Connect it. Connect the ground. So when you are done, so we have connected all the circuit together, but we have not assigned values to this component. Let's start from this. Right click the voltage source, click on advance. Since it's a sinusoidal waveform, we click this button for the sinusoidal waveform. DC offset, you are told to use the value of 0, amplitude of 1 volt, that is 2 volt peak to peak, frequency of 500 Hz, and every other thing can be left like that. Then the value of the resistance is 10 kilo ohms. So you put 10k, then the value of the capacitor is 0.01 UF, 0.01 microfarad. So you have set the values. Then you now want to run a simulation. So you go to, it's either you go to simulate, or you click on this guy that is always on the run. You click on it. You want to run a small transient analysis, a simple transient analysis of this circuit. So let's say you need 10 milliseconds. Time to start saving the data is, let's say, 1 milliseconds. Now, to choose this value is not difficult. It's not a rocket science. What you consider is, number one, the frequency you have set is 5000 Hz, and if you have set 5000 Hz, that will leave you with a period of 0.002 seconds. No, frequency is 1 over period. Period is 1 over frequency. If the frequency is 5000 Hz, definitely if you punch your calculator, 1 divided by 5000 will give you 1 divided by 5000 will give you 0.0002. So 0.0002. So that's 2 milliseconds. 0.002. Let me check. 0.00. One divided by 0.002. What am I pressing? 1 divided by 0.002 is 500. So it's 500 Hz. So 0.002 is our period. So that 0.002 is 2 milliseconds. So that's the period. So, and we want it to start saving before that one complete cycle. That was why I set time to start saving data to be 1 millisecond. Stop time after 10 milliseconds, you should stop. By that, you have gotten enough data to visualize. So when you have done that, you click on OK. So when you have clicked on OK, you now want to measure the voltage. Let's first of all measure the voltage supplied by this system. Click your cursor around here. The waveform will appear. So when you want to measure the frequency, what will you do? To measure the frequency, let's try to maximize this waveform so that we can have a better look. And when you look at the waveform, it runs from 0, minus, back to 0, to 1, and so on and so forth. So to run the frequency, just try to take your cursor, click on this voltage representatives here, then you try to track the point where the signal is. When the signal get to 1 complete cycle, this is 1 complete cycle now. 1 complete cycle happens from 0. Let me try to do one funny thing here. Let me try to invert this waveform. So I think like this it will be easier for us to work on. So from 0 to 1, back to 0, to minus 1, then back to 0. So this is 1 complete waveform now. So from this point to this point is 1 complete oscillation. So at this point, what is the value? It's almost 2 seconds. No, 2 milliseconds. That's at the point where you get 1 complete oscillation. It's 2 milliseconds. It's 2 milliseconds. It's already here. You can bring out this guy to see the time. That's 2.005 approximately. That's almost 2 milliseconds. So if you got the period to be 2 milliseconds, if you take your calculator, you can easily punch your calculator to get 2 milliseconds is 1 divided by 0.002. That will confirm that the frequency is 500 Hz. So that's how to measure frequency of an AC signal. Okay, so now from the laboratory, you are still told, because the first step is to measure the frequency, to confirm the frequency, which we have just done. So the other steps, we are to measure the phase angle. Like the step 2 says we should measure the connect the channel 2 of the oscilloscope and measure VC to measure the voltage across the capacitor. That one is as simple as anything. Just go back to the system, the voltage across the capacitor. Let's stop this simulation. If I stop this simulation, I want to measure the voltage across the capacitor. You click on your run again. So voltage that will be across the capacitor, let me click on it again. So the voltage across the capacitor is going to be the voltage here. So, but you have to be careful. Once your mouse turns to something like what you are seeing, like the arrow is pointing directly on the line, you are measuring current at that time. But it has to be, once it turns to something like a probe, that is when you are measuring voltage. So if I click on this is the voltage. When you check the two voltage, you discover that they are not the same. You can see one is taller. The one with the blue, which is the voltage across the resistor, that is almost equivalent to the supply voltage, is blue, which is, that one is having a peak amplitude value of 1 volt, but the voltage across the capacitor has reduced. So, but though they both have the same frequency, so let's just delete one of the waveform. Let me delete the blue so that we can measure the phase angle. To measure the phase angle, we have to measure the phase difference between the voltage and the currents. So this is a voltage waveform on the screen. So I want to measure the current. So I will click my cursor inside. Remember, this is a series circuit. The same current will flow through all the components in this circuit. So it does not matter where I put the cursor. If I put it inside here, put it inside here, put it inside here, we are getting the same thing. So this is the current. So the blue now represent the current, while the green represent the voltage. So we now want to measure the phase angle. So let's try to maximize the wave. I want to get I want my work to be limited to at least one cycle. So this is the voltage, this is the current. The current is the blue, white voltage is the green. So how do we measure that? The formula is this. Let me quickly write out the formula. Formula for finding the phase angle is TD divided by T, that is capital T, multiplied by 360 over 1. Remember, the total angle in a cycle is 360 degrees. TD is the time difference. Then capital T is the period of the waveform. So we are going to see how we get those two parameters. So when you look at this waveform now, what we do is, you want to know the time difference between the point at which this one get to its peak and the point at which this one get to its peak. That will give you the phase angle. That is the phase angle between the voltage and current. By what angle is the current leading the voltage? And vice versa. By what angle is the current leading the voltage? So the current is green, the voltage is the current is blue, while the voltage is green. So let's try to bring down two cursors. If you right click this one, make it number 1, that's the blue. Let me make it the first cursor, then the second one. If I right click this one, no, I want this, I think, let me make this one the first cursor. Let me make this first cursor. Okay, then make this one the second cursor, cursor 2. Okay, so we now have two cursors on the screen. So if you click, each of them will be tracking one waveform. Okay, let me bring it back. Okay, so I want this one is track. Which one is this one tracking? Okay, this one is tracking the current, while the second one is tracking the voltage. So let me try to make this. I prefer let me close this and resimulate. Let me resimulate so that it will be better again. So let me resimulate. Okay, I ran into a problem, This is the voltage, then the current. The current is blue while the voltage is green. So I want to let me maximize the waveform. So I want to just work like, let's work with just like one complete cycle. So I want this one to be the blue to be my first cursor, which is cursor 1. Then I want the green to be my second cursor, cursor 2. Okay, having done that, so let's try to track and see what each of them is tracking. So this one is tracking the voltage. This one is tracking the voltage. Then this other one is tracking the current. The other one is tracking the current. So the other one is tracking the current. So when you look at it, so you can bring this to the fore, so that it's unfortunate there's no way for me to expand this so that you all can see what I am trying to measure. So now phase angle is the simple way to explain what we mean by the phase difference is this. Now when you look at this point, at this point that the current has gotten to its maximum, the voltage is still rising at that point. That means there's a difference. That is, the current is leading the voltage. Remember, this is a capacitive circuit. So at the point that this one has gotten to its peak, this voltage is still struggling to get to the peak until it gets to this point where it gets its own peak. And at this point, this one is already going down. That's the concept of phase angle. So let's try to be sure that this one is actually the maximum value we can get. So on the current axis, I'm seeing 29.95, 29.92, 29.95, 958. I think the highest I can get is 29.959 microamps. Then for the voltage axis, let me check. I am getting 999.7, 99.96, 99.96. I think 99.96 is the highest I can get. So this is the peak of this. So when you look at the two of them from this cursor display, it will show you the cursor difference, cursor 2 minus cursor 1, which is 408.84956 microseconds. That's the time by which the current axis is leading the voltage. The current waveform is leading the voltage waveform. It's leading it by 408.849 microseconds. So let's try to work that one out. So the time difference TD. You can use any, whether small letters or capital letter. TD is let me get it again from the waveform. 408.849 408.849 multiplied by times 10 to the power minus 6. That's a microseconds. Seconds, microseconds. Then the period, capital T is equal to 0.002 seconds. So then the theta is the formula is theta equals to phase angle equal to TD divided by T, then multiply by 360 degree. So let's use our calculator to punch this value. So if you convert this 408.849 to microseconds, it's going to give you 0.1234408 seconds. That's 1 2 3 4 5 6. That's 1 2 3 4 5 6. So 0.0000408.408849. So that's the value in seconds. So this is the value in seconds. So if you put these values in your calculator, you now see that it's going to give you the phase angle, that is theta, that is TD, which is 0.123/0.000408849 divided by the period, which is 0.002, give you this one, then multiply by 360 degree, give you 73.59. So the phase angle theta equals to 73.59. So that's the phase angle between the voltage and the current. I hope this video helps. So if you have any questions, you have any comments, observations as concerning the videos or the formulas that I used or the method I used in getting the parameters, you can always write your opinion on the comment section and reach out to me now, and I promise any comments that have to do with video, I will always take time to respond as early as I can. Thank you very much for watching, and please do well by subscribing to this YouTube channel so that you can get up-to-date videos, informations as they come. Thank you. That will be all for now.